Hello guys, welcome back to my channel. And in this video, like the past couple of videos, and I know this may get annoying for some of you guys, that's why I have less views on those videos, but I'm actually again going to solve the Basel problem. But this video is particularly special because this is a Gamma Digamma special. I don't think this method has been uh, on YouTube, has ever been on YouTube before. So it's really exciting, guys. There's going to be complex analysis, there's going to be regularization, whatever that means. So let's get started. Okay, so like always, I should write what the Basel problem is, but I'm not going to do that. I'm going to do like a sort of sidetrack in this introductory lemma part. So consider the integral from 0 to infinity of say x over e to the x minus 1 dx. How can we solve this? Well, without any arguments, I'm going to write e with a negative power. So I have x times e to the negative x divided by 1 minus e to the negative x dx. All I've done is just written e to the x is 1 over e to the negative x. Okay, and that, now notice that e to the negative x, when you plug in 0, is going to be 1. And e to the negative x, when you basically take the limit as x tends to infinity, is going to go to 0. So e to the negative x is less than or equal to 1 and greater than or equal to 0. So if we let e to the negative x be our radius, our common ratio for a geometric series, we can see because of this fact that it is certainly within the radius of convergence. So we can use the formula for the infinite geometric series. So we can write this sum from n equal 1 to infinity, because the first term is e to the negative x that's present on top, and we have x times e to the negative x times n dx. So assuming uniform and absolute convergence, interchange the sum and the integral, we have sum from n equals 1 to infinity, integral from 0 to infinity, x times e to the negative nx dx. So now integration by parts, sum from n equals 1 to infinity, negative x times e to the negative nx over n, evaluated from 0 to infinity, minus minus plus integral from 0 to infinity, e to the negative nx divided by n dx. So at infinity, this exponential term is going to dominate this linear term, and everything will go to 0. And for the 0, the exponential will become 1, but the polynomial, the x term, will become 0. So this thing will just go to 0 regardless of what stuff you're plugging in. So now we have, when we evaluate this integral, negative sum from n equals 1 to infinity, e to the negative nx over n times n, which is n squared, evaluated from 0 to infinity. So at infinity we'll have a 0, and for a 0 we'll have a 1. So that negative and this negative will cancel out with sum from n equals 1 to infinity of 1 over n squared. And that's precisely our Basel problem. s. So this integral actually is equal to s, which we are interested in. So now going forward, I'm going to be exploring different avenues of calculating this integral. Okay, so s is equal to integral from 0 to infinity of x over e to the x minus 1 dx. Now what we're going to do is actually have this written in terms of complex stuff. So we can have integral from 0 to infinity of z over e to the z minus 1, where z is some complex number, and f of z we'll just call the integrand, which is z over e to the z minus 1. Okay, now all we need for a thorough complex analysis is a contour. Okay, so here's the contour we want. So we're going to start with a negative r, then go to this value that's called negative epsilon, just before this semicircular arc over here, then go across this semicircular arc like that, and then end at epsilon, and then from epsilon you go up to r on this linear path, and then from r what you do is you loop back to negative r to complete the path. So I'm going to call this gamma, this path gamma. Okay, and this path from negative epsilon to epsilon, I'm going to call that alpha. So our entire contour integral f of z dz can be expressed as integral from negative r to negative epsilon f of z dz plus integral over alpha of f of z dz plus integral from epsilon to r of f of z dz plus finally the integral over small gamma of f of z dz. Okay, so that's the entire breakup of things. Now just before moving on to other things, I would actually like to note that from minus r to negative epsilon we are completely on the real axis, so all z's are equal to x's, because the y, the imaginary component, is completely zero for this integral and this integral. So I would like to make that substitution in quickly. Integral from negative r, negative epsilon, f of x dx. Now I'll just substitute f of x, x over e to the x minus 1 dx. Then I'll write this alongside it. Integral from epsilon to r, x over e to the negative x minus 1 dx plus these two, integral over alpha f of z dz plus integral over small gamma of f of z dz. Now what I'm going to do further is look at these two separately on a fresh page, and it's going to be sort of like an estimation lemma. So let's do that. Okay, so this is basically the contour we have. First, let's look at integral over alpha of f of z dz. So making substitutions for f of z, we have integral over alpha of z over e to the z minus 1 dz. Okay, and I'm going to let, just to write the path integral, the line integral, we would have to make some parameterizations. So let z be equal to the radius of this path, which is epsilon times e to the negative I t, and negative because we are going in a clockwise manner here, a clockwise path will always have a negative angle associated with it. So we're taking care of that here. And t is basically going from 0 to pi because it's a semicircle like that. dz is negative epsilon I e to the negative it dt. So making those substitutions in, we now have 1 being equal to integral from 0 to pi of negative I epsilon squared e to the negative 2it, this is just multiplication in the numerator, divided by e to the epsilon e to the negative it minus 1 dt. And in the case you were wondering why I have this small indentation over here, that's because at 0, at z equals 0, e to the 0 is 1, so 1 minus 1 is 0. So there is actually a pole, there's actually a singularity at z equals 0, and we don't like to deal with singularities on the contour. I mean, inside the contour it's fine, outside the contour great, but on the contour not so great. So we try to avoid that, this singularity marked in red. So doing a few simplifications, we have negative I integral from 0 to pi 2 epsilon e to the negative it over e to the epsilon e to the negative it dt. Now what I'm going to do is I'm going to take the limit as epsilon goes to 0 because we want to make this alpha path as inconspicuous as possible. So doing that, we have basically a denominator. You can take the limit in because of linearity and continuous functions. 2 epsilon e to the negative it over e epsilon e to the negative it dt. Well, the denominator will have e to the 0, which is 1, and the numerator will be 0, making this entire integral go to 0. So 1, our integral over alpha, just turned out to be 0. Now we need to consider integral over small gamma. So call that 2. Integral over small gamma of f of z dz. But this is where we actually do the estimation lemma. So we need the mod of this, which is basically mod of integral over gamma of z over e to the z minus 1 dz, and that by inequalities is less than or equal to integral over gamma of mod of all the things that are inside. So mod of z divided by mod of e to the z minus 1 and mod of dz. So you can split the mod over division and multiplication like this. Okay, now it's again time for parameterizations for this path gamma. So for this, I'm going to have z equals r times e to the I tau. R because the radius is now r, this bigger path. That will make dz ri e to the I tau d tau. And tau again will go from 0 to pi. So with that we have integral from 0 to pi of r e to the I tau over e to the r times e to the I tau minus 1, and then dz is just mod of ri e to the I tau. You can take d tau out of the mod because it's basically just going to be an angle, it's positive all the time. So now by the inequality of mod of z1 minus z2 is greater than or equal to mod of z1 minus mod of z2, and then when you take the reciprocal you flip the inequality. By that, this is less than or equal to integral over integral from 0 to pi of, well, e to the I tau will just become 1, the mod of that. Mod of r is just r, Same thing here, mod of I is 1, e to the I tau 1, so r squared like that. And this inequality we want to use for the denominator, so this will be mod of e to the r times e to the I tau minus mod of 1, which is 1, and we have a simple d tau like that. Now what I'm going to do is I'm going to take the limit as r goes to infinity. This path has to basically go to infinity. So again, using convergence and linearity, r squared over e to the r e to the I tau under mod minus 1 d tau. Well, we have infinity over infinity situation, so if you want to use L'Hopital's rule, you can go ahead and do that. Just have integral from 0 to pi, limit as r goes to infinity, 2r over e to the r times e to the I tau times modulus of e to the I tau d tau. Well, the mod of this will go to 1. If you want to do L'Hopital's again, you can do that. Limit as r goes to infinity, you'll just have a 2 over same thing, mod of r times e to the I tau times mod of e to the I tau d tau. This goes to 1. So you have 1 over infinity, in this case 2 over infinity situation, which has to go to 0. So the mod of integral over gamma is equal to 0, and since a mod less than equal to 0 rather, because we were maintaining this inequality all the time, and since a mod can never be negative, it's either greater than 0 or greater than or equal to 0 or less than or equal to 0. So by the squeeze theorem, this mod is trapped between 0 on both sides. So this integral in itself will go to 0. So integral over gamma also went to 0. So all the inessential things just went to 0. Isn't that nice? Okay, so what that means in the greater scheme of things is this goes to 0 and this went to 0. And we also had taken two limits. We had taken the limit as epsilon goes to 0 and the limit that r goes to infinity. So I want to do that on both of these integrals over here. The other stuff just went to 0. So when I do that, I have integral from negative infinity to 0 x over e to the x minus 1 dx plus integral from 0 to infinity x over e to the x minus 1 dx. Now what I'm going to do on this first integral is make a quick substitution. Let x change to negative x, and doing that now we obtain integral from 0 to infinity negative x over e to the negative x minus 1 dx, integral from 0 to infinity x over e to the x minus 1 dx. We have integral from 0 to infinity of x over 1 minus e to the negative x dx plus, well, this in the introductory lemma just turned out to be the Basel problem S. Okay, now we can do a little more work again by the same logic that e to the negative x is going to lie between 0 and 1 on 0 to infinity. We can again use the infinite geometric series from n equals 1 to infinity, but we don't have a first term. So what we're going to do is we're going to have x and e to the negative x raised to the n minus 1 this time, not n, because we don't have a first term dx plus s. So again, interchanging these two things, sum from n equals 1 to infinity of, well, x times e to the negative x times n minus 1 over negative n minus 1, which is 1 minus n, evaluated from 0 to infinity, negative, negative, positive, integral from 0 to infinity, e to the negative x n minus 1 over n minus 1 dx plus s. Well, at infinity again, exponential will make it go to 0. At 0 again, linear term will make it go to 0. So this is 0. We just have sum from n equals 1 to infinity of, well, negative e to the negative x times n minus 1 over n minus 1 the whole thing squared, evaluated from 0 to infinity. This is just basic anti-differentiation going on here. So at infinity it will go to 0, at 0 it will go to 1, but with a negative. So that negative, this negative goes off. We have sum from n equals 1 to infinity of 1 over n minus 1, but the whole thing squared, plus s, and that is precisely equal to our contour integral of f of z dz. But there is actually a way of calculating this contour integral out separately in a way that's called the residue theorem. So let's do that on a fresh page. See you there. Okay, so for residue theorems, we're interested in something that are called poles. And poles are basically looking at the original integrand function, the values where the function becomes undefined. Undefined for finite values. So that means making the denominator 0. So that means e to the z minus 1 should be equal to 0, which means e to the z is equal to 1. And there are many ways of doing that actually. So if z is 0, e to the 0 is 1. And if you remember this formula, e to the I theta is cosine theta plus I sine theta. We can actually have that. So for example, 2 pi I, e to the 2 pi I is cosine 2 pi plus I sine 2 pi. Well, sine of any integral multiple of pi will be 0. Cosine of an even multiple of pi is always 1. So we have that. And then 4 pi I by a same argument. Going on till we can generalize this to say 2n pi I, where n is some integer. N is some positive or negative integer, anything. Okay, so these are all the possible values where this function could blow to infinity. So all of these are poles. Now for the residue theorem, we need to only care about the poles that are inside the contour. So just reminding ourselves what the contour actually is. That's the contour. Okay, so z equals 0 is over here, and that's way outside the contour, right? We chose to basically bypass that with this alpha path. So forget 0. Z equals 2 pi I is somewhere over here on this imaginary axis. 4 pi I is on top of that, twice the distance. 6 pi I likely this way, and since this r, this outer casing of radius r, we let that go to infinity in the limit when we were basically doing estimation lemma and also the integration. Because of that, we can accommodate inside the contour an infinite number of poles excluding 0. So we can accommodate 2 pi I, 4 pi I, and going on till infinity. So the list of poles is as follows: 2 pi I, 4 pi I, dot dot dot, 2n pi I in the limit that n goes to infinity. So infinite number of poles can be accommodated inside because it's an infinite radius, outer radius contour. And now what we're going to do is find the residue at each of those points. So let's take 2 pi I. So residue at z equals 2 pi I. And noticing it's a simple pole, because if you differentiate the denominator, you'll have e to the z, plugging in 2 pi I, e to the 0, which is 1, and which is not equal to 0. Basically tells us that it's a simple pole. So e to the z minus 1 was in the denominator. We differentiated that, e to the z, and then plugged in the pole value, 2 pi I. So 2 pi I is equal to, well, 1, which is not equal to 0. If this was equal to 0, it would not have been a simple pole, but it's a simple pole in our case. So to calculate simple poles, what we do is we take the limit as z approaches 2 pi I, z minus 2 pi I times f of z. So limit is z goes to 2 pi I, z minus 2 pi I, z over e to the z minus 1. Well, we can write 1 as e to the 2 pi I and notice we have a derivative in the denominator over here. We have e to the z minus e to the 2 pi I over z minus 2 pi I in the limit as z goes to 2 pi I in the denominator mainly. And this is actually the derivative of e to the z evaluated at 2 pi I. So derivative of e to the z is just e to the z evaluated at 2 pi I. So e to the 2 pi I is going to be 1. So this goes to 1. So we have limit as z goes to 2 pi I of z. So that is going to be 2 pi I. And this holds true for any pole. So the residue at z equals 4 pi I is going to be 4 pi I by the same arguments. So the residue at any general 2n pi I is going to be 2n pi I. And how is this helpful? That's because the contour integral of f of z dz is actually equal to 2 pi I times the sum of residues that's inside the contour. And if you're asking, well, we could have taken the negative integers as well. That we're not doing that because negative integers would be outside the contour. They would be below over here in the negative imaginary axis, and that's outside the contour. So we ignore the negatives and the 0, just positive integers. So now, to sum over all residues, we can start the sum from n equal 1, go to infinity because we can accommodate an infinite number of them, and have 2n pi I like that, right? Because when n is equal to 1, we have 2 pi I, which was the first residue, and so on and so forth. So now we can actually factor out some things. We have negative 4 pi squared sum from n equals 1 to infinity of n. That's the contour integral of f of z dz. Okay, fair enough. Okay, so finally tying stuff together from our contour and estimation lemmas, we got that the contour integral of f of z is sum from n equals 1 to infinity of 1 over n minus 1 squared plus the Basel problem. And from residue theorem, we got that the contour integral of f of z dz is actually nothing but negative 4 pi squared is equal to times sum from n equals 1 to infinity of n. So to basically equate both the sides. Negative 4 pi squared sum from n equals 1 to infinity of n is equal to sum from n equals 1 to infinity of 1 over n minus 1 whole thing squared plus s. And now in case you're wondering, the left hand side clearly diverges, because if you start writing this sequence, you'll have 1 plus 2 plus 3 plus 4 going on till infinity, basically sum of all positive integers. And well, there's an infinite number of them, and they basically get larger, they don't decrease. So this should diverge, right? This should diverge. So sum of some series is equal to, well, infinity or divergence. Well, the thing is, if you plug in n equals 1 over here in this series, 1 minus 1 is 0. So we have 1 over 0 the whole thing squared, which is again infinity. So in essence, just because of that n equals 1 term, we are going to end up with a divergence. So we're going to have divergence equal divergence, or infinity equal infinity. So it's not all that illogical. Infinity equals infinity basically. But it's not the dead end. It's not the dead end. It's a new beginning. That's because if we choose to do something that's called regularization, that's basically bypassing the divergences, we can actually come to a really, really nice answer. So how do we bypass the divergences? So, just neglect or just assume that, well, the one part, when n equals 1, when n equals 1, 1 over n minus 1 the whole thing squared is 0. If we assume that, then this just becomes minus 4 pi squared sum from n equals 1 to infinity of n is equal to sum from n equals basically 2 to infinity, because 1 just turned out to be 0. So 0 plus other terms, 1 over n minus 1 the whole thing squared plus the Basel problem. This, by reindexing, turns out to be sum from n equals 1 to infinity of 1 over n squared plus s, which is basically the Basel problem again added with the Basel problem. So 2s is equal to minus 4 pi squared sum from n equals 1 to infinity. Now I can write n as 1 over n but raised to the negative 1 power. And I'm doing that because remember the Riemann zeta function of, say, s is defined as sum from n equals 1 to infinity of 1 over n to the s. So we essentially have, for our purposes, the Riemann zeta of negative 1 over here. And now, interesting part about the Riemann zeta function in a process that's called zeta regularization, or you can call it analytic continuation, is you can use Bernoulli numbers to actually extend the jurisdiction of the Riemann zeta function. So Riemann zeta of negative n can be expressed as minus 1 to the n Bernoulli, the n plus 1th Bernoulli number divided by n plus 1. I'm not going to get into detail with Bernoulli numbers, but if you plug in 1 in place of n, you have minus 1 to the 1, minus 1, the Bernoulli number of 2 divided by 2. Now the Bernoulli number of 2 happens to be 1 over 6, and there are ways of doing that. I'm not going to get into details. So the Riemann zeta of negative 1 is actually negative 1 over 2n. So just for regularization purposes, the sum of all positive integers in a way, and I'm putting sum under quotes, is minus 1 over 12. And you can get the same result by a Ramanujan summation formula. So there's no surprise there. This entire proof is actually reverse engineering the Ramanujan summation formula, but it's still unique in its own way, because We just incorporated complex analysis into it. So this, forgetting this was just scratch work. We have negative 4 pi squared, and then this was just Riemann zeta of negative 1 is equal to 2s. But this, as I said, has a value of, we calculated that negative 1 over 12 is equal to 2s. The negatives cancel out. 2s is equal to pi squared over 3. S is therefore equal to pi squared over 6. Isn't that wonderful? Just wonderful. I mean, all the trouble we went through of complex analysis that we had over here, and all the regularization, considering different infinite residues for a change, two estimation lemmas, and finally we get the beautiful answer of pi squared over 6, all because of regularization and complex analysis. So thank you guys for watching. I hope you learned a lot as much as I did. I think that's a good place to end the video now. So before going, please like, share, and subscribe to my channel. Recommend me to your friends. Spread the word of Gamma Digamma in the community. I'm putting in a lot of work for these videos, guys. And for the 100 subscribers, thanks again. I will be. I could do a Q&A with you guys if you just comment some questions for me to answer, and if you request hard enough, I might even do like a face reveal or something. So anyways, stay home, stay safe, keep doing math, peace out, and I'm signing off.